Now, whenever we work with models, one of the first questions that comes up, and of course we have a global weirding episode about this as well, but one of the first questions that comes up is, can you trust the models? So that's what part 5 is about. Can we trust the climate models? Well, there's a famous statement by a statistician, all models are wrong, but some are useful. And that is certainly true. In fact, those of us who study climate models are more familiar with their warts than anyone else, because that's what we're constantly looking for. But there's a lot of misconceptions related to climate models that often lead people to evaluate or to judge them incorrectly or inaccurately. So I want to point out what climate models are supposed to do and what they're not supposed to do. So first of all, weather versus climate. We already talked about how climate is the long-term average of weather over at least 20 to 30 years, whereas weather is what happens in a certain place at a certain time. Weather prediction is like predicting a certain tree. There's a 30% chance of rain. There's a 30% chance of the tree growing to this height. But climate projections are like looking at the average statistics of the forest. Some trees might be taller, some might be shorter, some might be older, some might be younger. But climate is the average statistics of the whole forest together. Now, weather models and climate models are based on the same physics for sure. But weather models are initialized with observations, whereas climate models are spun up over centuries until they develop their own patterns of natural variability, and then they're what we call forced with their inputs. They're forced with either historical observed forcing, like changes in energy from the sun, volcanic eruptions, and human emissions of heat-trapping gases, or they're forced with the future scenarios. So this is really important. Climate models are not trying to predict the weather. They're not trying to predict the weather next week, next year, or next decade. Yes, a climate model will have a value, an output value for June 18, 2032. But is it accurate? No. You need to look at not just one day in June, but all the days in June. You need to look at not all the days in that June, but all the days in 20 years of Junes to get some idea of how the mean values are changing, how the variance is changing, and how that affects both the average and the extremes. Those are what we call climate because they are the statistics of weather. So for example, I've actually seen people take, 10 climate models and say, I want to pick the best climate model. And I'm working in the upper Midwest where there were massive heat waves that really affected our systems in 1995 and 1999. So I'm going to go through these 10 climate models and I'm going to see which climate model has a massive heat wave in 1995 and 1999. And those are obviously the best models, so I'll pick those. Well, here's the problem with that. The problem with that is that models each have their own pattern of natural variability. As you can see here, a climate model, these are all the different names of different climate models here. Don't worry about what the acronyms stand for. They're very dense. These are all different climate models, though. They all have the same continents. They have the same sun. They have the same volcanic eruptions. They have the same human emissions. But they have their own chaotic patterns of natural variability, such that the real world might have had a heat wave in 95 and 99 over the upper Midwest. But the CCSM model might have one massive heat wave in 1991 and another in 2005. The INMCM model might have one in 1995, but then not another one until 2010. Does that mean that one model is better than the other? No, because what these are climate models, not weather models. So what you have to do is you have to look at the statistics of the heat waves or the weather that you are looking for in each model over a representative time period, which is at least 20 to 30 years. And when you look at that, for example, over the upper Midwest, as I recall, it's been a while since I worked in that area, but as I recall, I think almost every model we looked at had one extreme heat wave during that period. So in other words, they can produce the statistics of weather, but they're not supposed to, they're not intended to, and they're not designed to produce the exact weather that occurs in the real world. So when we evaluate climate models, we don't want to do that. We don't want to say, did they produce the flood of 2011 or the heat wave of 2012? We want to say, do they have the statistics of weather? And in the same way in the future, that's what we want to look at. Now, we can look at climate models and how they have performed over large spatial scales, like a continent or the entire world, and over decadal timescales. And there's this great article here by Carbon Brief that I highly recommend taking a look at if you're interested. I'm just going to give you one result from it, but it's got a lot more results in there, where they took very early historical climate model projections, the first ones that actually progressed through time, because Arrhenius's didn't progress through time. So the first climate model projections actually progressed through time, and they compare them with what has happened afterwards. So for example, Jim Hansen, who many of you may have heard of, he did some of his very first climate projections in 1981. He worked with two scenarios, scenario 1 and scenario 2, he called them back then, very straightforward. You can see the thick black line is scenario 1, the thin gray line is scenario 2. And then what are the bumpy lines? The bumpy lines are the actual observed global average temperature as calculated by the different data sets from around the world, one from NASA, one from the UK, one from NOAA, etc. So you can see that in the real world, there were ups and downs, hotter and colder, but long-term global temperature gradually ticked up, just like the climate model. And again, we're talking about a 40-year-old climate model here. So in the Carbon Brief article, they actually go through a whole set of models. It's really amazing. I strongly recommend taking a look at it. But I'm going to jump ahead to where we are today. Where we are today is we have climate models that now have all of that natural variability in them. So you can see that the climate models here, the orange is the range of all the different models. So instead of showing each line for each different model, they just show the range, because otherwise it would look like a spaghetti diagram and you couldn't see anything. The range now has a lot of bumps and wiggles in it. Why? Because the models now have natural variability in them, which they didn't used to have back in 1980. So by that I mean they have El Nino, they have natural cycles, they actually have weather systems in the model, and they didn't have that 20 years ago, or 40 years ago I should say. But at the same time, you still see pretty much the same result. The observations go up and down from year to year, that's weather, but decade by decade by decade, they gradually tick upwards, and so too do the projections. So why are future projections uncertain? We've already started to talk about this a little bit, but I want to bring it all together. The first reason is that climate models have gotten pretty good. We've been doing it since the 1890s. That's a long time. That's over 130 years. But they're not perfect. They have many flaws. They have many faults. We're constantly improving them. Also, we have the problem that natural variability is chaotic. So rather than having identical planet Earths, it's as if we have multiple planet Earths, each with their own patterns of natural variability. On one Earth, you might be having a storm one day. On one, you might be having a drought. On one, you might be having an El Nino event. Natural variability is uncertain, and the smaller the time scale you look at, the more important it becomes. And then we've got the human factor that we talked about in the last part. Future scenarios are driven by human activities, and we can't predict human behavior. And then last of all, we have the fact that we're conducting a truly unprecedented experiment with our planet. As far back as we can go in time, we can't find another time when this much CO2 was going into the atmosphere this fast. And so we have a pretty good idea of how the planet is already responding and how it's likely to respond over the next century. But there could, as we talk about here in Chapter 15 of the National Climate Assessment, which I also recommend reading, there could be some nasty surprises. So let's talk about each of these very briefly. I'm not going to dwell too much on future scenarios because we already talked about that in detail in the previous part. But let's start with how climate models are not perfect. Well, there's two very specific types of uncertainty in climate models, and the first type is known as structural uncertainty. This consists of the structure of the model. Do we have all the physical processes in the model that we need to? For example, the processes that explain how the Greenland ice sheet is melting 6 times faster today than in 1990. And the answer to that is no, we don't have all those processes in because we don't even understand some of them yet. So do we have all the important physical processes in the model? And are those physical processes correct or not? So in other words, are there pieces of physics or chemistry that we're missing? Or are there pieces that are in the model that aren't accurate? That's structural uncertainty. The second source of uncertainty in climate models, though, is parametric uncertainty. And this means that in a model where an average grid cell in the model, remember how we divide the whole Earth up into these little boxes, the average grid cell could be like 100 by 100 kilometers per side. But within this grid cell, we are trying to model things that are tiny. Like what? Like cloud droplet particles that determine rain. We're trying to model tiny, tiny little things at a gigantic scale. And so rather than actually including the physics that explains how raindrops form and fall, instead we have to use parametrizations of the physics that are roughly approximately accurate over the scale of the grid box, which could be 100 by 100 kilometers. So these are the two biggest sources of uncertainty. Then we have the fact that natural variability is chaotic. Now remember I showed you all those different planets, right? Well, now I'm going to show you what the average temperature on all those different planets looks like. And it really is a spaghetti diagram. This is a set of data that we prepared for Delaware. The black line is the observed temperature in Delaware, Wilmington, Delaware, from 1960 to 2010 for every year. And then the colored lines are all the different planet Earths, or all the different climate models. Now you might look at this and you might say, first of all, your rough impression might be the climate models are crap. None of them really track the black line. I mean, if I was going to pick one model, maybe I'd try to find one that sort of tracks the black line, but honestly, I don't even know which one that would be. Well, here's the thing. Your eyes would be deceiving you because that's not what we're looking for here. What are we looking for here? We're looking for two things. First of all, do the climate models capture the range of natural variability seen in the observations? In other words, if you drew an upper and a lower line on the climate model lines, would that upper and lower line look similar to the upper and lower line of variability on the black line? And the answer there is actually yes, it would. So how warm and how cold it gets from year to year and decade to decade in the real world is reproduced quite well by the climate models. In fact, if anything, the climate models are slightly higher in a few places. You can see on the left-hand side, you see the purple lines are a bit lower and then the green lines a little bit higher. And that would be expected because you only are looking at 50 years here. Whereas with the climate model simulations, you've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. You've got 9 different climate models times 50 years. So you have a much bigger sample. So you would expect the range of variability in the climate models to be a bit larger because you have a bigger sample. So that's number one, and that's good news. What's the second thing that we would use the climate models for? Again, we're not using them for predicting what happened in 1992. We're using them to predict what happens over climate time scales, which is the average of temperature over 20 to 30 years. So we can use them to look at the long-term trend. And when we use them to look at the long-term trend, as you can see here in the very thick red line, you can see that the long-term trend is reproduced very well by the climate models. So a diagram that originally looked like a big mess actually shows us that the climate models are pretty good at reproducing the variability as well as the long-term trend, but it also shows us that you can't just use a climate model for 1 year or 2 years or even 10 years because you could end up with something that bears no resemblance to reality. That's because they're climate models, they're not weather models. We have to use their output over climate timescales. Then we had the issue of future scenarios, which we talked about in the last part. And lastly, we have the fact that we are conducting a truly unprecedented experiment with our planet. Now, this plays into that second point. Remember I talked about how the first source of uncertainty are our human choices, and the second source of uncertainty is what is the planet going to do in response? Why don't we know? Well, we do know the direct impact of producing the methane and the carbon dioxide and the heat-trapping gases. We can measure the direct impact. We've been able to measure it since the 1850s. But what happens is once we put heat-trapping gases in the atmosphere and they start to trap heat, that actually triggers some feedbacks in the climate system. And the feedbacks are what add that extra layer of uncertainty. How strong are the feedbacks? Where do the feedbacks come from? And how strongly do they respond to the warming? Like what? Let me give you a few examples. One of the feedbacks that we know is clouds. We know that as humidity increases, we could be getting more clouds forming. But here's the thing. If the clouds are lower down, they reflect more sunlight and they can actually cool the planet down. But if the clouds that form are higher clouds, they actually trap more heat because the clouds are colder, and so they would warm the planet up. So whether it's a self-reinforcing feedback where it gets a little bit warm and then the feedback makes it even warmer, or whether it's a negative feedback where it gets a little bit warm and the feedback makes it cooler, it depends on how and where the clouds form. That gets pretty tricky, doesn't it? In the Arctic, we have a lot of feedbacks, and unfortunately in the Arctic, most of those feedbacks are amplifying feedbacks. In other words, the warmer it gets, the stronger the feedback, the warmer it gets. Those are what we call vicious cycles too. So that's why the Arctic, remember I said Arrhenius found this in 1890? That's why the Arctic is getting warmer faster than the rest of the world, because it has these positive feedbacks. Positive feedbacks, of course, is a tremendous misnomer, because if I gave you positive feedback on your journal article, that would be good, wouldn't it? In reality, again, I think the best thing to do is to call these self-amplifying feedbacks, or possibly even vicious cycles. And one of the ones in the Arctic is the fact that most of the Arctic is covered in a fairly reflective substance, ice or snow. It is quite reflective in that most of the sunlight that hits ice or snow gets reflected back to space. But what happens as it gets warmer? Arctic sea ice is melting. When you look at it like this, it becomes even more obvious. So the ice reflects about 50 to 70% of the incoming solar radiation, whereas when the ice melts as it gets warmer, what happens? The dark ocean absorbs 94%. So a lot more of the sun's energy is all of a sudden being absorbed by the Arctic, which means the Arctic has even more energy, which means it heats up even faster, and that's not all. No, the poor Arctic has a lot more going on. And one of the other self-amplifying feedbacks it has is related to heat-trapping gases. So in the Arctic, there's a lot of permafrost. Permafrost is permanently frozen ground, and it contains a lot of organic material that has never decayed. What happens when that permafrost thaws? The organic material decays. It produces heat-trapping gases, methane and carbon dioxide, and those heat-trapping gases leak out of the permafrost into the air, where they trap even more heat. That is a big self-amplifying cycle. What does this look like? Well, I had the opportunity to actually visit the University of Alaska Fairbanks this past year and spend some time with Terry Chapin. You can see Terry there on the right-hand side in the plaid shirt. And with Katie Walters, who studies methane from permafrost, and they took us to one of Katie's study sites. She studies the methane that bubbles out from the sediments at the bottom of the lake. She normally collects the methane in the winter because the ice acts like a trap on top of the lake. It traps all the methane. But she rigged up this really cool little experimental setup with materials that she actually originally found in Siberia in the garbage, where if you stir up the mud in the bottom of the lake, it will, that you can't see, but she has a kind of a plastic tarp in the water, and it will trap the gas that comes up, and the gas will be guided into that upside down bottle there. It builds up at the very top. At the very top, she has a stopcock, and when you've had enough gas build up at the top, because natural gas is mostly methane, you can actually open that stopcock and you can light the gas on fire as it comes out of the bottle. That's how you know it's methane. Not only that, but as the permafrost thaws, we're getting huge holes in the ground. Terry is actually standing next to one of those holes. We're getting drunken trees as the root systems no longer have solid ground to hang on to. And wherever you go around Fairbanks, there is the bumpiest road you've ever seen, and there's road construction almost constantly, because the permafrost also has large ribbons of ice running through it. In some cases, they might be just a few centimeters wide. In some cases, they can be 1 meter or 2 meters wide. And when those ribbons of ice melt, all the ground above them slumps. So you can see the visible impacts with your own eyes, but what you cannot see, unless you go with Katie to her experimental sites, you cannot see the invisible gases that are leaking out of the thawing permafrost, trapping even more heat in the Arctic. So why are future projections uncertain? They're uncertain because our models aren't perfect, because natural variability is chaotic, and these aren't weather prediction models, because future scenarios are driven by our choices, and because of these feedbacks in the climate system. But here's the interesting thing. Work by Ed Hawkins and his colleague Rowan Sutton. You probably know Ed because he designed the warming stripes. He also designed the warming spiral that was used in the opening ceremony of the Brazil Olympics, which is amazing. But he also creates a bit more scientific graphics as well. And this one graphic he created, I think, is so clear. It shows how the type of uncertainty that is most important depends on the time frame that you care about. So if you are only looking over short time frames, the scenario doesn't matter hardly at all if you're looking over 10 to 20 years. What matters is the scientific uncertainty and natural variability. If you're looking at precipitation, scientific uncertainty is much more important because you have a lot of parametric uncertainty going on, right? Trying to model raindrops, tiny little raindrops in giant global climate models. Whereas if you're looking at temperature-related changes, human choices rapidly become important because they're driving the massive changes in temperature that we see. So the bottom line is the type of uncertainty that matters most really depends on what you care about and what you are looking at. If you care about what happens over the next 10 to 20 years, then natural variability is most important. And what you want to do is, it doesn't really matter which scenarios you want to use as many climate model simulations as you can. Remember that spaghetti diagram from Delaware of all the different colored lines? You want to use as many simulations as you can. They can be from the same climate models, because some climate models run 10 different ensembles or 10 different simulations in their ensemble, or you can also combine multiple climate models, but that'll give you the biggest range of uncertainty and natural variability. So beyond 20 to 30 years, human choices become most important for temperature-related impacts and for drought and extreme precipitation over larger spatial scales. This is where we absolutely want to use a range of future scenarios, at least a higher and a lower one, to encompass possible outcomes. Because, if you recall, higher amounts of change show us what we could avoid by reducing our emissions, and lower amounts of change, lower scenarios, show us what we can't avoid and we're going to have to adapt to no matter what. And in Chapter 4 of the National Climate Assessment, which I've already recommended as reading, I talk about how I often take those RCP scenarios, or those SSP scenarios, and I actually break them down into temperature thresholds. Because the Paris Agreement is not in terms of a given scenario, it's in terms of 1.5 or 2 degrees. So what you can do, and this is explained in more detail in the National Climate Assessment, is I actually have a lookup table where for each different climate model and each different scenario, I know the first 20-year period when that simulation hits 1.5 degrees, 2 degrees, 3 degrees, and 4 degrees. And so what I can do is I can slice and dice the different simulations so I can put together a look of what happens to a given place and a given variable when the world warms by 1.5 or 2 or 2.5 or 3 degrees. For some climate models, they say that's going to happen sooner. For others, they say it'll happen in a bit longer. For a higher scenario, it'll happen sooner. For a lower scenario, it'll happen a bit longer. But I can actually look at what a 1.5 versus a 2 or 3 degree world looks like. And that has the advantage of tying this directly to the Paris Agreement. So over the next 10 to 20 years, natural variability matters the most. Use as many climate model simulations as you can, and also look at historical observations too. I'm not telling you to take your eye off the rearview mirror entirely. I'm telling you to fix at least one full eye ahead, and maybe one full eye or almost one full eye behind you too. Beyond 20 to 30 years, you want to make sure that you look at multiple future scenarios, especially when you're looking at temperature or extreme precipitation related variables. But beyond 20 to 30 years, scientific uncertainty is often most important for precipitation, especially over smaller spatial scales. And so for that purpose, you want to use as many climate models as you can, because there is no one perfect or set of perfect models. There isn't. Now again, I understand. There is a great temptation to try to identify the best models. And often, even if we don't do something like taking a model and saying, does it reproduce the 1995 heat wave over the upper Midwest? Often what we do is we say, well, let's look at the models and see which ones get the right variable for, or the right range or number for precipitation in spring over our region, or something like that. But here's the problem. First of all, we know that climate models have a bias or an offset compared to the real world that is mostly due to their spatial resolution. The higher spatial resolution the model has, the lower the bias, though it doesn't totally take it away. The other thing we know is that just because a model might not reproduce the right value, it doesn't mean it doesn't simulate the change. And what are we using the models for? We're using them to simulate the change. So sometimes in some places, if the studies have already been done, and they might take, a scientist who's an expert in atmospheric dynamics 1 or 2 years to do the study, if the study's been done showing that a certain climate model or a certain set of climate models don't actually have a physical process in them, structural uncertainty, right? They don't actually have a physical process in them that you need at that region. So for example, especially in the previous generation of models, not today, but 10 years ago, there were some models that couldn't reproduce a North American monsoon. They just couldn't do it. So if you were studying an area that was affected by the North American monsoon, you would have a reason not to pick the best models, but to exclude the turkeys, as I call them. Exclude the ones that really don't have what you need. And similarly, up in the Arctic, they had a problem where some of the models really didn't have the physical processes in them that they needed to simulate the melting of sea ice, which, as you saw, is very important to determining how climate change affects the Arctic. So for that reason, there were some models that you did not, at that time, want to use in the Arctic. Now, most of those problems have already been fixed. Most climate models do have all the pieces in them that they need. And in fact, my own research has shown something very interesting that I want to share with you very briefly. I won't get into it in too much detail. If you're interested, you can go ahead and read the paper. The paper was published in Climate Dynamics in 2017. It's Ryu and Hayhoe. But in this, we looked at how climate models are able to simulate precipitation over the south central United States. So you've got Texas in the middle, you've got Oklahoma on top, you've got Louisiana off to one side, and New Mexico off to the other. And we looked at that greater region and we said, we know that our precipitation has a very distinct bimodal pattern. We know that we have a wet season in spring. The observations are the black line. The reanalysis is the red line. Reanalysis is a weather model fed by observations. And then the blue lines are all the different climate models. So we know that we have a wet period in spring, beginning mid-April to mid-June. Then we have a midsummer drought. And then we have a brief, smaller wet period in the fall, and then we go into the dry winter. So this is what happens in the observations. And when we looked at the climate models, we found that about 2/3 of the climate models did capture that structure. In other words, they captured the summer and then the drought and then a little wet peak and then the decline. But 1/3 of the models didn't. They just had one giant wet season and they had no dry period in the middle of the summer. We also know why that happens. There's an actual physical feature that shows why that happens. And that physical feature is called the North Atlantic subtropical high. So in the winter, the North Atlantic subtropical high, which is a semi-permanent high pressure system, is parked off in the Atlantic. But in the summer, it moves over the southwest. And as it moves over us, a high pressure system suppresses convective activity and it directs storms away from our region. So our midsummer drier period is caused by the presence of the subtropical high pressure system over us. And then when it starts to retreat back to the east in fall, that's when we get that brief wet period. So there's an actual physical system. And what we found is, as you might imagine, the climate models that reproduce the bimodal pattern, as you can see here, those climate models got the North Atlantic subtropical high coming over at roughly the right time with about the right strength. But the ones that had one big wet season, they had the high pressure system in them, but it wasn't strong enough to suppress the rain. So it was too weak. So based on this, at this point, you might be saying, okay, you identified the turkeys, get rid of them, right? Not so fast. We decided to look at the future projections from both of those sets of models. Now, this figure is a little bit complicated. I apologize. We atmospheric scientists are known for our rather dense figures. What you're looking at here is you are looking at a cross-section, not in geography, but in time here. So we are going from April to September here on the x-axis, but then, to make things even more confusing, we are going in space from 20 degrees north to 45 degrees north on the y-axis. And what you're seeing here is you're seeing two things. You're seeing how the North Atlantic subtropical high pressure system moves over our area. That is the contour lines, the black contour lines. So you can see that it's strongest in July and August, and then it weakens again as you go out into September. You can see that the extended wet season models in the bottom, they don't have it strong enough. It's much weaker, just as we said. And then what the colored area is it is the wind, it's called the Great Plains lower level jet, that is actually bringing moisture from the Gulf of Mexico up to our region. And that moisture is the source of a lot of our precipitation. So based on this figure, which is historical simulations, you would say, oh, well, clearly one set of models is better than the other. But let's run it forward into the future and see what we get. Ready? When we run it forward into the future and we slice them up by degree of warming, like I just talked about briefly before, and we look at what would happen in a world that is 1 degree warmer than today and 2 degrees warmer than today, we see the same changes happening in both sets of models. Both sets of models show the Nash arriving earlier and being much stronger and more persistent on average than they were in the past. So it didn't matter if it was a bimodal model or GCM or not, or I should say if the GCM got the bimodal distribution or not. It didn't matter because all the models, every single one of them, showed the Nash getting stronger. And in fact, when we dug deeper into it in subsequent studies, we found that this was because of a self-reinforcing feedback. It's because as the ocean warms, the North Atlantic subtropical high was passing over the Gulf of Mexico before it reaches Texas. You can kind of see how it would do that. It would go over Florida and then over the Gulf of Mexico, then Texas. And because of all that high, the much warmer water, it was actually strengthening the subtropical high. So this was happening, this physical process was happening in all the climate models. But we never would have looked at that process if we hadn't looked at the projections for the future and seen that all the models showed the same thing. So when we're looking at drought over the south central US, there are no turkeys. We're not taking any turkeys out. You might have said we'd be taking out the one set of models, but we aren't. And that's why picking the best set of models is very risky. And in fact, what the science has showed is this. The science has showed that there is no one perfect model. Even if there was one for one variable for one region, if you're looking at a different variable, it might be a different model. But if you use as many of them as possible together, it's more likely to be closer to reality than any single individual model or small subset of models. What else do we know about uncertainty? We know that climate projections from the models should always be used over climate timescales, the statistics of weather over at least 20 to 30 years. We know that future scenarios are driven by human activities, which we can't predict. So we always have to look at the future as an if-then. If we do this, then this is likely to happen. And if we don't do this, then this won't happen. And lastly, we have to recognize that there is always the chance of surprise. And that is why the further and the faster we reduce our carbon emissions, the better off we'll all be.